I think we are going to practice some more, but I'd like to discuss the slant asymptotes now. For rational functions. So, as we know, there are three types of asymptotes. We already encountered here two of them, vertical, horizontal. So vertical and horizontal. But there is one called slant. Slant means oblique, something like this, or something like this. Notice that the function, this is a vertical asymptote because the function eventually follows it. The function eventually follows it. Again here, eventually follows it. We say asymptotically approaches such and such, follows it. So the same thing with the slant. So if we find that the function has a slant asymptote like this, let's say y equals x, the function eventually has to follow it, either from above or from below, we don't care, but it has to follow it. I don't have the function. We're going to choose a function in a minute. But it's the same idea. So eventually, so you cannot graph the function away from the asymptote. So eventually towards infinity has to follow it. Towards negative infinity has to follow it. So that's the idea of the slant asymptote. Which functions have slant asymptote? And one other note. No rational function has vertical and slant asymptotes. No, one or the other. Either vertical or horizontal. It cannot have both. So we can have the combination vertical with horizontal. We can have the combination vertical with slant. But we cannot have the combination slant with horizontal. It either approaches, for pure rational functions, either approaches a horizontal line or approaches a slant line. It cannot approach both, because these are both at infinities. That's what we are discussing. So the horizontal asymptote is towards infinities, and the slant asymptote is also towards infinities. If it approaches infinity, it cannot approach 3. If it approaches negative infinity, it cannot approach 5. So it cannot happen. So slant with vertical, yes. Vertical with horizontal, yes. But slant with horizontal, no. So now I'm going to share my screen and look at one thing before I let you choose, I have to mention which functions have slant asymptotes. Only one type of rational function. Only if a rational function has degree n and degree n plus 1. In other words, if this is degree 2 and this is degree 3, the function will have a slant asymptote. If this is degree 1 and this is degree 2, the function will have a slant asymptote. If this is degree 5 and this is degree 6, it will have a slant asymptote. So what I'm saying is the degree in the numerator has to be by exactly 1 unit higher than the degree in the denominator. Exactly by 1 unit higher. So now let's choose one and find the slant asymptote and the behavior, where it's going. So that's why I cannot find them. I know why I cannot find them. Because I don't know if I was in 4.5. I think I was. Okay, I think I was, yeah. So we're going to look at some rational functions. And we're going to select one that has a slant asymptote. Use the guidelines of ... We only want to focus on the slant asymptote right now. So find an equation of the slant asymptote. So do not sketch. So we have from 65 to 68, and we have from 69 to 74. As you notice, these are special. These are not rational functions. The analysis was for the rational functions. Other functions have slant asymptotes as well, but our analysis so far was about rational. See here, rational, degree 3, degree 2, slant asymptote. Degree 3, degree 2, slant asymptote. Degree 2, degree 1, slant asymptote. Degree 2 and 1, slant asymptote. 4 and 3, yes. 3 and 2, yes. 3 and 2, yes. 2 and 1. So because the rational function that has a higher degree in the numerator by 1 unit, higher than the degree in the denominator, will have a slant asymptote. So let's choose and find the slant asymptote. Okay, I will choose 67. And I will write it 2x cubed minus 5x squared plus 3x, always in descending order, both top and bottom, x squared minus x minus 2. So for this problem, in this problem, we are only asked to find the slant asymptote. So degree 3, degree 2, it will have a slant asymptote. So we will use the long division. There is no other way for this particular problem. So I have 2x cubed minus 5x squared plus 3x. Notice that one term is missing. The terms have to be in descending order, and if this term is missing, I have to leave a space. Or put 0. I don't like that, but you can put 0. But degree 3 is there, degree 2 is there, degree 1 is there, just degree 0 is not. And I'm dividing by x squared minus x minus 2. So the first question is, x squared is multiplied by what to get 2x cubed? X squared times what is 2x cubed? And I put the expression here, the term. What do I write?
2x.
Yes,
2x.
2x indeed. So 2x times x squared is 2x cubed, but remember we have to subtract. 2x times negative x is negative 2x squared. We have to change the sign. 2x times negative 2 is negative 4x. Change the sign. Always write below like terms. Nothing. Negative 3x squared plus 7x. I should bring down the next one, but the next in line, but there is nothing. Final question. X squared times what is negative 3x squared? Here we're not lying, so to speak. Here we have to. 2x times x squared is positive 2x cubed, but I have to subtract. 2x times negative x is negative 2x squared, but I have to subtract. And 2x times negative 2 is negative 4x. I have to subtract. But here we're not lying, up here. X squared times what is negative 3x squared?
Negative 3.
Negative 3. I have to distribute now, changing the sign. Negative 3x times 2x times x squared is negative 3x squared, but I have to subtract. Negative 3x times negative x is positive 3x, but I have to subtract. Negative 3 times negative 2 is positive 6, but I have to subtract. So this is 4x minus 6. So the function can be represented by this, or quotient plus remainder over the divisor. So quotient 2x minus 3 plus remainder 4x minus 6 over the divisor. x squared minus x minus 2. This is the slant asymptote. Y equals 2x minus 3 is the slant asymptote. Since the slant asymptote has a positive slope, the limit of the function at positive infinity will be what? What do you think?
Positive infinity.
Yes, it has to follow the function. And the limit as x approaches negative infinity of y will be what?
Negative infinity.
Negative infinity. And it's clear. Why? Because at infinity, this piece at positive or negative infinity, where will this piece go? What do you think? Look carefully. At infinity, where will this piece go? Not this.
To 0.
Of course, because the degree at the top is much smaller than the degree of the bottom, so this will approach 0. That's why we are not erasing it. That's why it's not, doesn't have any influence on the slant asymptote, because it's approaching 0. That's how we determine slant asymptotes. Any questions on how to find the slant asymptote? Okay. Would you like to choose another function to graph, or can I continue and then we'll go back to graphing more after we finish? Any preference? Okay, in that case, I will continue with 4.8 Newton's method. I did not forget about L'Hopital's rule and the other, but this should not take long. Okay. So Newton's method is a procedure that helps us, that enables us to solve any equation. Any equation. There are many equations that we do not know how to solve. Many. So I will illustrate on an example, and I let you choose an example. It doesn't matter which example. And I will explain the method, and then we'll solve it. No one can solve this by hand. 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 These are impossible by hand. So let's choose one. Would you like the arctangent or something else? You choose. I will explain the method after we choose the example, any example. Anyone?
22.
Okay, 22. 22 is x cubed equals 5x minus 3. Perfect. Okay. Good. Now, let's suppose we have a function. This is f of x. And as you see from my graph, it has a solution. F of x has a solution. F of x equals 0, better, it's correct to say f of x equals 0 has a solution, or f of x has a 0, or f of x has a x-intercept. They all mean the same thing. If I say that the solution, let's call it root r. If I say the function has an x-intercept, or I say has a 0, in other words, f of x is 0 when x is r, or this equation has a solution, number 1, number 2, number 3, they all mean the same thing. And here's what Newton did. I'm going to graph this again and zoom in even more. So he said the following. Show me an open interval, a 1-unit open interval, that a function that is continuous changes sign. And we have that IVT, intermediate value theorem for continuous functions. And I find an open interval, a comma b, 1 unit interval, or smaller, but 1 unit is fine, a comma b, where the function is continuous, of course, and it changes sign. IVT guarantees that there exists a c in the open interval a comma b such that f of c is 0. We discussed this a long time ago in chapter 2 under continuity, intermediate value theorem. And we said then, what is the problem with this? IVT cannot give us the solution. But IVT guarantees that there is a solution as long as the function is continuous and it changes sign from negative to positive or from positive to negative. Now, Newton's method will help us determine the solution. But first, we have to start with the IVT. We have to start by saying the function is continuous if it is, and what is the interval? We have to put in the graphing calculator and determine a 1-unit interval. And then we will say by IVT there is a solution. So I can start the method. So in our case, I'm going to share my screen. Go to y equals. In y equals, clear everything I had. I don't care for this anymore. And remember, solving this equation is like solving that equation. I will move everything to one side. So then I have x cubed minus 5x plus 3 equals 0, because I need to identify the function. So therefore, this is my function. F of x is x cubed minus 5x plus 3. Is it continuous? Yes, it's a polynomial function. Once I find the interval where the function changes sign of 1-unit interval, then I can start the method. So for our function, I will put it in as is, x cubed, and then minus 5x, and then plus 3. And I will just go to second and table, and I plug in some numbers. Hopefully the solution is not between 1,500,000 and 2 million or something, right? So I'm hoping that I'm starting slow with 0 and with 1. Oh, that's good enough. That's all I needed. You may have other solutions. I only want 1. So I see that the function is continuous. It's a polynomial function. I see it changes sign between 0 and 1. IVT guarantees a solution between 0 and 1. So I'm going to write this as the preliminary step. So f of x, continuous, as a polynomial function on 0, 1. F of 0 is positive. F of 1 is negative. Is that what it was? Yes, positive and negative, correct. So therefore, I would write by IVT, there exists a c c in the open interval 0, 1, such that f of c is 0. So I know there is a solution. So these are the absolute first steps. We have to find the interval. And we find the interval only for a continuous function, and only if I find a 1-unit interval where the function changes sign. And we did. So now, brilliant Newton said this. So this is the 1-unit interval 0, 1. I'll make it huge so I can explain what I'm trying to do here. Okay. So here's the function. Actually, as you saw, this is not the function because it's coming from positive to negative. It doesn't matter. I'm just illustrating the method. So here's our c or root, doesn't matter. We need to start with x0, the initial value. It doesn't matter if I choose to start with 0 or if I choose to start with 1, as long as some conditions are fulfilled, and I will explain the conditions. I'll explain them in a minute, not just now. So in principle, it doesn't matter where I start with 0 or 1 as my initial value, as long as the conditions I will explain in a minute or two are fulfilled. So let's suppose we start with 1. Newton said this: go up vertically, if I can, vertically. Can I draw a vertical line? I think I can. Okay. Determine this point. Well, very easy. 1, f of 1. 1, comma, f of 1. And from there, draw a tangent, of course. The whole thing is about tangents, right? So I'm going to draw a tangent to the graph. I'm going to extend the tangent till it crosses the x-axis. Can I determine this point? Yes. I will call this point x sub 1, comma 0, because this was x sub 0. This was the initial value that I started with. This is my first iteration, x sub 1, first iteration. Let me see how I'm with time.